morning everyone. Today we are going to see neuro-adaptive control of robotic systems. The outline of this lecture will be as follows. First we are going to see about filtered error approximation based control. Then we have adaptive control of robotic systems, and we have neuro-adaptive control of robotic systems. So, let us talk about approximation based controllers. We all know that computer torque control which is given by the control law tau equal to alpha tau dash plus beta, where tau dash is the servo law and alpha is B of q, which is the inertia matrix, and beta equal to C of q comma q dot into q dot plus G of q. So, with this computer torque control scheme, it works very well provided all the dynamical parameters such as B of q, C of q comma q dot and G of q are known accurately. Then only this computer torque control will work well. But in the case of robotic systems, these parameters vary with time and are also not properly known. So, the control objective is to achieve trajectory tracking under parameter uncertainty. That is a control objective, because for the robotic system these parameters vary with the time or they are also not known accurately. So, the control objective for us is to achieve trajectory tracking task under parameter uncertainty. So, there are two approaches to deal this. One is adaptive control, another one is robust control scheme. So, in this lecture we are going to see adaptive control followed by neuro-adaptive control. Then we will see what is filtered error, because the topic we are going to cover in the first part is filtered error approximation based controller. First of all, filtered error, it is given by R equal to E dot plus lambda E, where E is a tracking error given by QD minus Q is the error between the desired joint trajectory and the actual joint trajectory. That is called the tracking error. Whereas lambda is a positive definite design parameter matrix. Lambda is a positive definite design parameter matrix. Now, taking the Laplace transform for a scalar case, we get E of s equal to R of s upon s plus lambda. So, that is giving you the error where the tracking error E can be obtained by passing this quantity R, which is a filtered error, through a low pass filter, and hence the name. Okay, so again the tracking error E can be obtained by passing this quantity R through a low pass filter, and hence the name. So, this kind of error representation leads to a simplified controller design owing to the model reduction or the system order reduction. Next, coming to this boundedness of this errors. Let us talk about boundedness of the filtered error ensures the boundedness of tracking error as well as the time derivative of the tracking error. Thus, tracking error norm is bounded by norm of R upon the minimum singular value of matrix lambda, and E dot is bounded in such a way that it is less than equal to the norm of R. Thus, the boundedness of R filtered error ensures the boundedness of both tracking error as well as the derivative of the tracking error, and also the desired trajectory is bounded such that Qd of t, Qd dot of t and Qd double dot of t is less than equal to Qb. Okay, so, the boundedness of both the error as well as the desired trajectories are seen now. Next, we will see how the dynamic model can be expressed in the filtered error. So, expression of the dynamic model of the robotic system in terms of filtered error R, that is given by Br dot equal to minus C of Q comma Q dot into R plus f of x minus tau, that is the dynamic model of a robotic system expressed in the filtered error R, where the non-linear robot function f of x is defined as f of x equal to B of q into Qd double dot plus lambda E dot plus C of q comma Q dot into Qd single dot plus lambda E plus f of q dot plus g of q, and we have the state vector x equal to E transpose E dot transpose Qd transpose Qd dot transpose Qd double dot transpose, entirely transpose, and f of x contains all the potentially unknown robot parameters, that is f of x. So, it is a non-linear function and it has all the unknown robot parameters. Okay. So, now we can move on to the continuation of approximation based control. Now, we are going to have the control law, that is called approximation based controller. Let us see that approximation based controller is given by a control law tau equal to f hat plus kvr minus v of t, where f hat is an estimate of f of x, and v of t is the robustifying term of this control law, and KVR is an outer PD tracking loop. So, outer PD control loop. Now, with this control law put in that equation, which is the dynamic equation in terms of the filtered error, we substitute back here in the previous equation, we get the closed loop error dynamics, coming out to be BR dot equal to minus C of Q comma Q dot into R minus KVR plus F tilde plus V of t. Now, there is something called F tilde, which is nothing but f of x minus f hat of x. So, that is called functional or function approximation error, that is f tilde equal to f minus f hat. There f is the actual function, f hat is the estimated function, and f tilde is given by the term function approximation error. Okay, so, now let us move on to the controller design problem statement. Now, let us talk about the controller design problem statement. Controller design problem. So, we need to select the estimate f hat and v of t, the robustifying term, in the above approximation based control law, in the above approximation based control law, such that the closed loop error dynamics is linear and stable, such that the closed loop error dynamics is linear and stable. So, for that we need to select the estimate f hat and robustifying term v of t to make the closed loop error dynamics linear and stable. Now, let us talk about adaptive control. Let us talk about adaptive control. Adaptive control of robotic systems can be applied, it can be applied to a class of nonlinear systems, that satisfy the following conditions, such as the system's full state is measurable, the nonlinear, then the second is the nonlinear plant dynamics can be linearly parameterized. Second condition is the nonlinear plant dynamics can be linearly parameterized. Then third one, the non-linearities can be cancelled stably. The non-linearities can be cancelled stably by the control input. Okay. If the parameters are known, if the system parameters are known. So, in this case the adaptive control can be applied. So, now let us rewrite the robot dynamics again in terms of the filtered error. We will be getting B r dot equal to minus C of q comma q dot into r plus f of x minus tau. Again I write this B r dot equal to minus C r plus f of x minus tau. C matrix depends on both generalized coordinate q as well as the derivative of it. So, I simplified that here without putting the input arguments of C matrix. So, where the nonlinear function here, the nonlinear function is f of x may be expressed as a linear function of unknown parameters such as f of x equal to b of q into q d double dot plus lambda e dot plus c of q comma q dot into q d dot plus lambda e plus f of q dot plus g of q is equal to w of x into phi, where w of x is known and it is called regression matrix. And phi is a function of or is a vector of unknown parameters. Okay. So, this is the situation. F of x can be represented by w of x into phi, where w of x is known regression matrix and phi is a vector of unknown system parameters. Now, one adaptive control law proposed by Slotin in the year 1988 is given by tau equal to w of x phi hat plus kvr, which is equal to f hat of x plus kvr, and we need to know about phi hat. So, that phi hat is obtained by phi hat dot equal to gamma w transpose of x into r, where gamma greater than 0 is a tuning parameter matrix, and we will be getting this expression for phi hat dot in terms of gamma w transpose and r by the Lyapunov stability analysis. So, the control law proposed by Slotin is tau equal to w of x phi hat plus kvr, where phi hat is obtained by the update law, which is given by phi hat dot equal to gamma, which is a tuning parameter matrix, w transpose of x into r, and this expression, say expression A, is obtained by Lyapunov stability analysis that we are going to see now. Okay. So, now the estimate of nonlinear function is given by f hat of x equal to w of x into phi hat, and due to linear in the parameter assumption, LIP assumption, we can have f tilde equal to f minus f hat, which is equal to w of x phi minus w of x phi hat, that is equal to w of x into phi tilde. Thus f tilde is given by w of x into phi tilde, where w of x is a regression matrix and phi tilde is given by phi minus phi hat, and f tilde is given by the function approximation error, which is given by f minus f hat. Okay, so now let us continue this. Representation of phi hat is given by phi tilde is given by function or the parameter estimation error. Parameter estimation error, that is given by phi minus phi hat. Okay, that is phi tilde. Now, the above adaptive control yields following closed loop aerodynamics. The above adaptive controller yields the following closed loop aerodynamics in terms of filtered error, that is B r dot equal to minus C of q comma q dot into r minus kvr plus w of x into phi tilde. Now, let us select the Lyapunov function candidate. That is given by L equal to half r transpose B of q into r plus half phi tilde transpose gamma inverse phi tilde. One is the first term of this Lyapunov function candidate is basically the error term, which is a filtered error term, and another one is the function approximation error term. It is the parameter estimation error term in the second term of Lyapunov function candidate, and the first term is filtered error term. Let us continue this. So, here we can say that the lambda is a symmetric positive definite weighting matrix, where I can write here where lambda, this lambda is a symmetric positive definite weighting matrix, that is all. Now, let us go for the time derivative of the Lyapunov function candidate, that is given by L dot equal to half r transpose B dot r plus r transpose B into r dot plus phi tilde transpose gamma inverse phi tilde dot. Now, substituting the closed loop aerodynamics B r dot, we will be getting this L dot being half r transpose B dot r plus r transpose into B r dot, we are going to substitute, which is nothing but the closed loop aerodynamics, that is given by minus C of q comma q dot into r minus kvr plus w of x into phi tilde plus this third term phi tilde transpose gamma inverse, this is over, and the third term which is phi tilde dot. So, that leads to half r transpose B dot R minus R transpose C of Q comma Q dot into R minus R transpose KVR plus R transpose W of X phi tilde. It's phi tilde, okay, plus phi tilde transpose gamma inverse phi tilde dot. That can be given by having half R transpose taken out, we will get B dot minus 2C into R minus R transpose KVR plus phi tilde transpose taken out, we have gamma inverse phi tilde dot plus W transpose of X into R. Now, we can see that we have arranged this equation to this equation, so that we can have the skew symmetric matrix B dot minus 2C as per the properties of the dynamics of a robotic manipulator. Based on the skew symmetric property of this matrix B dot minus 2C, we can have X transpose multiplied by B transpose B dot into 2C into X equal to 0 for all X. So, we are going to have this first term on the right hand side being 0. So, we will be having this L dot going to become minus, it is going to become minus R transpose KVR. Okay. So, it is going to become minus R transpose KVR, which is going to be less than equal to 0. This is obtained, and now we have to check one thing, that the L dot transpose is obtained by the L dot, that is the derivative is obtained as negative definite, and in this case we have left with only this term, because we are having the second term which is evaluated by phi tilde dot equal to minus phi hat dot equal to minus gamma W transpose of X into R, where phi is a constant, that is why phi tilde dot is becoming minus phi hat dot, which is nothing but phi minus phi hat dot. So, phi dot is 0 because phi is a constant, and hence the inner bracket of the previous equation becomes minus phi or minus gamma inverse phi hat dot plus W transpose of X into R equal to 0 in the previous equation of L dot. So, this term must be 0, for which phi hat dot turns out to be gamma W transpose of X into R. That is what given along with the Slotin's control law for the update of phi hat. Okay. So, now substituting this back into the L dot equation, we finally end up with this equation, say B, that is L dot is equal to minus R transpose KVR, which is less than equal to 0, and therefore, R and phi tilde are bounded according to the Lyapunov theorem. According to Lyapunov's theorem. Okay. So, now we have to ensure that R of t tends to 0 as time tends to, we have to ensure R of t tends to 0 as t tends to infinity. So, one may use Barbellet's lemma to show that L dot goes to 0 with time. So, let us take the double derivative of L, that means derivate one more time of L dot. So, we get L double dot being minus 2 times R transpose kV R dot, and substitute the error dynamics here. So, we get in terms of B inverse. So, L dot with the substitution of error dynamics, closed loop error dynamics. Okay, so, we get L double dot equal to minus 2 times R transpose kV B inverse into minus of C into R minus kV R plus W of X into phi tilde, that is your L double dot. Now, the right hand side is bounded. Now, in the previous equation say C, the right hand side is bounded because of the boundary conditions of the manipulator parameters such as C matrix, B matrix, etc., and the demonstrated boundedness of R and phi tilde. Thus, I can say that the right hand side is bounded because of the bounded assumptions of the system parameters of the robotic system, which are B matrix, C matrix, etc. And also previously we demonstrated that R, the filtered error, and phi tilde, the estimation error, parameter estimation error, phi tilde, are bounded, and hence we can say L double dot is bounded, which implies that L dot is uniformly continuous, and by Barbalat's lemma we can say that L dot tends to 0 as t tends to infinity. Thus, one can say that R of t tends to 0 as t tends to infinity, that is all. So, now we move on to the neuro-adaptive controller, that means adaptive control based on neural networks. Let us see that, that is neural network based adaptive control. This is the major portion of today's lecture. Again, let us say, or let us express the dynamic model of the robotic system in terms of the filtered error R. So, it becomes BR dot equal to minus CR plus f of x minus tau. Now, choose the control law as tau equal to f hat plus kV R, where f hat equal to w hat transpose phi of x, with f hat being an estimate of f, where f I represented basically small f of x. Let small f of x be represented by f hereafter. So, f hat is an estimate of the function f of x, which is capital F, which is basically function of non-linear parameters. So, here in neuro-adaptive control, a neural network is used to approximate this non-linear function f. So, the control law can be written again as tau equal to w hat transpose phi of x plus kvr. Okay. So, now the closed loop error dynamics is going to become, with this control law and the dynamic model, the closed loop error dynamics is going to become B r dot equal to minus C r plus F minus W hat transpose phi of x minus k v into r, which implies B r dot equal to minus C r plus W hat phi of x minus k v r minus W hat transpose phi of x, since f of x is given by W transpose phi of x. Simply we are representing f by W transpose phi of x in the second equation. Therefore, B r dot becomes minus C r minus k v r plus W tilde transpose phi of x, which is say equation number 1, where W tilde is given by W minus W hat. Okay. So, now consider the Lyapunov function candidate L equal to half R transpose B r plus half trace of W tilde transpose gamma inverse W tilde. Therefore, time derivative of this Lyapunov function candidate L dot being R transpose B r dot plus half R transpose B dot R plus trace of W tilde transpose gamma inverse W tilde dot, which implies R L dot equal to R transpose, substituting the closed loop aerodynamics in this equation L dot. So, we get R transpose equal to this L dot equal to R transpose multiplied by minus C r plus minus C r minus k v r plus W tilde transpose phi of x and remaining terms plus half R transpose B dot R plus trace of W tilde transpose gamma inverse W tilde dot. Okay. So, now we are just expanding the equation of L dot, and then in this equation again we have C matrix, B matrix. So, B dot and C. So, as per again the skew symmetric matrix property of the skew symmetric matrix, B dot minus 2 times C will give 0. So, upon simplification with the same skew symmetric matrix property of B dot minus 2 C, we have R transpose multiplied by B dot minus 2 C into R equal to 0 in the previous equations expansion, and from the properties, from the property of trace or matrix trace, we can say that R transpose W tilde transpose phi of x becomes trace of W tilde transpose phi of x into R transpose, that is row matrix multiplied by column, row matrix multiplied by a column matrix can be written in terms of trace as trace of column matrix multiplied by row matrix. So, with this property of matrix trace, we can represent R transpose W tilde transpose phi of x equal to trace of W tilde transpose phi of x into R transpose. Thus, L dot becomes minus R transpose k v r plus trace of W tilde transpose phi of x R transpose plus original trace of W tilde transpose gamma inverse W tilde dot, which finally leads that L dot equal to minus R transpose k v r plus trace of combining trace of W tilde transpose phi of x R transpose plus W tilde transpose gamma inverse W tilde dot, where W is constant. So, W tilde dot is going to become minus W hat dot. So, we are going to have the expression for L dot is going to become minus R transpose KVR plus trace of W tilde transpose into phi of x R transpose minus gamma inverse W hat dot, since W tilde dot equal to minus W hat dot. Okay, this is it. So, this middle term phi of x R transpose minus gamma inverse W hat dot equal to 0. So, to have this entire term 0. So, this term to be 0 means you are going to get W hat dot is equal to gamma phi of x R transpose, that is the thing. So, in that, with this expression of W hat dot, L dot is going to become minus R transpose KV R, which is less than equal to 0. Now, L double dot again we have to go for it 2 times R transpose KV R dot, and we can say that L dot of, so L dot is going to become 0 with t tends to infinity, and finally by Barbalet's lemma, as in the case of adaptive control, we can say finally that R of t vanishes, okay, because of the boundedness of the system parameters. That is, here we involve B inverse of q. With the boundedness of B inverse of q and all the signals associated with the closed loop aerodynamics, it can be verified that R and, that is R dot and L double dot are bounded. That leads to R tends to 0 as time tends to infinity. So, with this I conclude that in this, so coming to the conclusion, we can say that in this class we have seen filtered error, approximation based control of robots, precisely adaptive control of robotic systems, and third one neuro-adaptive control of robotic systems. So, in the neuro-adaptive we had W that is obtained from the weight matrix of the neural network, weight matrix of neural network, and phi of x is basically the transfer function of the neuron or the activation function associated with the neurons of the neural architecture. Thank you so much for your time.